Assalamualaikum and hi. Today we are from Group 5 from section RA12 are going to representing our work-based project, which is piping system. Our lecturer is Dr. Hasmani binti Abdul Halim, and this is my group member, which is the first one is Li Yikai. The RA is 25087, and the second member is Wan Amrul Wajidi bin Wan Kamaluddin. The RA is 25088, and the third one is me, which is Muhammad Khairul Iqbal bin Maskuri. The RA is 25090, and the last member is Muhammad Ammar Daniel bin Osman. The RA is 25091. Our introduction is a domestic water supply piping system invented for ensuring smooth and reliable water flow in a swimming pool. The system efficiency depends on proper pipe layout, design, appropriate pipe diameters, elevation difference, and the number of rating used. Poorly designed piping networks can lead to excessive head loss, pressure drops, and inefficient water circulation. This can lower filtration effectiveness and rest energy use. In this project, we analyze a swimming pool water circulation piping system using fluid mechanics principle. Water is drawn from skimmer and main drains and transported through a PVC piping network to a pump, filter, heater, and salt cell before returning to the pool. The system includes horizontal and vertical pipe section, various bend, teeth, and control valve, as shown in the layout. We consider two piping configuration, which is an initial layout and an improved layout. The initial design was hydraulically inefficient due to many sharp bends, long and high pipes, and significant elevation change, which all increased frictional and minor loss. Based on this finding, we propose an improved piping layout. The recommended are increase diameter of pipe, add skimmer, and optimize the routing of suction and return lines to improve overall hydraulic performance by minimizing head losses and enhancing flow distribution among system components. The improved layout ensures more efficient pump operation, better water circulation, and increased energy efficiency. This makes it suitable for detailed fluid mechanics analysis and practical application. And our objective is to evaluate the hydraulic performance of the existing swimming pool water circulation piping system by analyzing flow path, pipe diameters, fitting, and elevation change to identify sources of head loss and inefficiency in the initial piping layout, including the effect of sharp bends and elevation difference on pressure drop and flow distribution. To design an improved piping layout that optimizes the routing of suction and return line to lower pipe head, reduce the number of fittings, and smooth transitions to lower frictional and minor loss. And the last one is to compare the initial and improved layouts in the term of hydraulic efficiency, pump operation, water circulation, effectiveness, and potential energy saving.
Assalamualaikum and hi. So today I will explain the functions of the things that we put in the drawings. For the first one, which is pump, it is used to circulate water through the filtration and heating system. For heater, it raises water temperature for comfort. The next one is filter. It removes dirt, oil, and other particles from water. The next one is suction pipes, which used to draw water from the pool and convey it to the pump inlet. The next one is return pipe. It is to deliver water from the pump to discharge or back to the final destination. The next one is salt cell. It converts dissolved salt into chlorine using electrolysis. The next one is skimmer, which is to collect floating debris such as leaves, insects, and oils. And the last one is main drains. It is used to remove heavier debris and deeper water.
Assalamualaikum. I am Wan Amrul Wajidi Wan Kamaluddin, RA25088. At this part, I'm gonna tell more detail about how to get cash before and after our improvement. First, we look at the before our improvement. This is the water heater, water filter, water pump, and salt cell. This cache, the pipe diameter is 0.8, and we saw that at pool system, the pool take too much time took very much time for water to fill the pool. Here we look, we use elbow for every change direction, and here and then we use T. Then we look at front. We look at front view. And then side view. And then top view. Then we go at after our improvement. After our improvement, we add one skimmer, and then we add more pipe at here, and then we at here at bottom, and then at the top we add more pipe at the new system, and then we change the diameter of pipe to 0.5 meter, and then the filter, heater, pump, and salt cell are the same. And then we change the pipe here from the bottom and top. We use like this for make water not change a lot direction at here. And then we look at the front view, and then side view, and top view. And then that's all for my AutoCAD sketch explanation.
Good morning, my name is Ili Ikai, RA250X7. Today, I would like to present about calculation and assumption. The K value of entrance loss is 1, K value of elbow is 0.9, K value of exit loss is 1, K value of weft is 0.5, K value of T-joint elbow is 1. The flow rate is 0.03 meter cube per second. Power of pump is 700 watt. Total length of pipe before improvement is 430.74 meter. Total length of pipe after improvement is 463.48 meter. Part of friction factor is 0.015. Calculation before improvements. We use the diameter 0.5 meter. First, we find the velocity. Velocity equal to Q, which is flow rate. A, area, pi d squared over 4. So the calculation is 0.03 divide pi times 0.5 squared over 4. So we get the velocity is 0.15 meter per second. Then Reynolds number. Reynolds number equal to rho Vd over dynamic viscosity. Our rho is 1000 for water. Velocity is 0.15. Our diameter is 0.5. So that the dynamic viscosity is 1.75 times 10 power negative 3. So our Reynolds number is 42,855.14, which is bigger than 4,000, so it is turbulent. Next, hash entrance equal to K V squared over 2G. Our K value for entrance loss is 1. So 1 times 0.15, which is velocity, 1 times 0.15 squared over 2, 9.81. So our answer is 0.00115 meter. Then H elbows equal to K V squared over 2G. K value for elbows is 0.9 times 0.15 squared over 2 times 9.81. The answer we times 16 because we have 16 pipes. So we get the answer 0.0165 meter. H pipe friction equal to friction factor times length times velocity squared divide 2 gravity times diameter. So 0.015 times 430.74 times 0.15 squared divide 2 times 9.81 times 0.5. So equal to 0.0148 meter. H watts equal to kV squared over 2G. K value for watts is 0.5 times 0.15 squared divide 2 times 9.81. So equal to 0.00573 meter. HT joint equal to kV squared over 2G. So 1 times 0.15 squared divide 2 times 9.81. The answer we need to times 2 because there's 2 T joint. The answer is 0.023 meter. H axis equal to kV squared divide 2G. So 1 times 0.15 squared divide 2 times 9.81. The answer is 0.00115 meter. H pump equal to 700 times 1 divide 1000 times 9.81 times 0.03 equal to 2.379 meter. So total loss is sum of the total head loss. So equal to negative 2.343 meter. So calculation after improvement, we use diameter 0.8 meter. So for the same, we find the velocity first. Velocity equal to Q flow rate divided by area. So flow rate is 0.03 divide pi 0.8 squared over 4. So we get the velocity is 0.06 meter per second. Next, Reynolds number. Reynolds number equal to rho Vd divide dynamic viscosity. Rho, we use the 1000 for water. Velocity 0.06 times 0.8 diameter. So the whole divide by 1.75 times 10 power negative 3. So we get the Reynolds number is 26,428 0.57, so it's bigger than 4,000, so it is turbulent. Next, head loss for entrance, hash entrance. So the K value of entrance loss is 1, velocity is 0.06, so 1 times 0.06 squared divide 2 times 9.81, so we get the answer 0.0018 meter. Next, hash elbows. The K value for elbows is 0.9. 0.9 times 0.06 squared divide 2 times 9.81, and then the answer we times 16 because we have 16 of pipes. So the answer is 0.00276. H pipe friction, friction factor times length times velocity squared divide 2 times g times diameter. So 0.015 times 463.48 times 0.06 squared divide 2 times 9.81 times 0.8. So the answer is 0.00159 meter. H watt equal to kV squared over 2g. K value for watts is 0.5 times 0.06 squared divide 2 times 9.81. So the answer is 0.00009892 meter. HT joint equal to kV squared divide 2g. The H value for T joint is 1 times 0.06 squared over 2 times 9.81. The answer we should times 2 because we have 2 T joint. So the answer is 0.00037 meter. Next, H exit equal to kV squared over 2g. K value for exit load is 1 times 0.06 squared over 2 times 9.81. So the answer is 0.00018 meter. H pump equal to power of pump times pump efficiency divide rho, gravity, and flow rate. So 700 times 1 divide 1000 times 9.81 times 0.03. So the answer is 2.379 meter. So the total loss is sum of the total head loss. So equal to 0.2.374 meter. This is for after improvement. So energy losses and recommendation. From the calculation, it is already known that the piping system can carry out its function efficiently with bigger pipe diameter. After the improvement of increase the diameter of pipe in the system can reduce friction loss and increase flow capacity, allow more volume to pass with less energy. Inefficient piping system is before improvement negative 2.343 meter. After improvement, which is efficient piping system, we get negative 2.374 meter. So our group's recommendation is piping system that has been modified by increasing the diameter of pipe.
For the conclusion, this project evaluates the hydraulic performance of existing swimming pool water circulation system and identified inefficiencies caused by long pipe length, sharp bends, and elevation changes. These factors increased head loss and reduced flow efficiency. The improved piping layout was designed to reduce pipe length and the number of fittings, resulting in better pump performance, improved water circulation, and potential energy savings. Overall, the project shows that applying fluid mechanics principles can effectively improve system efficiency and performance. That's all from us, Group 5. Thank you.